worksheet today that we did in class. I just wasn't able to get everything to work in class to make this recording, so I'm going to do it right now. We're working on problems from section 7.3. And we're looking at trig substitutions. Which we use as a method of getting rid of radical signs when we have an integral that's not your basic u du integral. We'll encounter integrals that might have expressions that look like an a squared minus an x squared, in which case we're thinking of our trig identity that 1 minus sine squared gives us a cosine squared. So in order to get that to look like, to have a term that looks like this, we pick x to be a times the sine of theta, so that we'll have an a squared minus a squared sine squared. And once we factor out the a squared, we'll get to use this identity. But our integrals have a dx in them, so we also need to compute dx from this substitution. The derivative of sine is cosine, so our dx term is a cosine theta d theta. That'll help us take care of integrals that have an a squared minus x squared in them. If our integral has an a squared plus an x squared in it, in either order, then we're going to try to use the fact that tangent squared of theta plus 1 is equal to a secant squared theta, so that we can swap two terms added together to one term that's a perfect square. And so to do that, we take x to be a times tangent of theta, and dx will be, let's see, derivative tangent is secant squared theta d theta. So that goes with this, that goes with this, and then the other type of integral we'll encounter is when the x squared is in front of the minus sign. So for integrands involving an x squared minus an a squared, we're going to use this trig identity, but written in terms of secant squared theta minus 1 is tangent squared theta. So in this case, we pick x to be a secant of theta, and then dx is equal to a secant theta tan theta d theta. And these substitutions should allow us to get rid of square root signs that have terms like that underneath. So let me separate these so that they're easier to read. That one, and here's plan for this type of integral, and then the plan for the third type of integral. So we're hoping to change integrals that have these things in them into identities where we can get rid of the square root sign, and then maybe have a trig integral that we can do. So some of you have forgotten the following trig integrals. Let's recall these. These are the ones that we developed in section 7.1, that the integral of a secant of theta, secant to the first power, is the natural log of the secant of theta plus the tangent of theta. And the integral of a tangent of theta is minus the natural log of the cosine of theta. The cosecant and the cotangent work in a similar way. The integral of a cosecant of theta, d theta, has a natural log, but has a cosecant plus a cotangent, and it has a minus sign out front. And the integral of a cotangent, it has cotangent is cosine over sine, so it's just going to have a natural log of a sine. If we encounter any more that I need to add to this list as we do the example problems, I'll come back and put some more on here. But right now, this is going to be our cheat sheet to help us do the problems on our trig integral. So there's my sequence of integrals that I want to do, and I get you started out with how I want you to do these. So my first one has a plus sign between the x and the number. So that's why I suggest that we use a tangent in our substitution. And after we square the x, we need to have the same number in front of the tangent. So that's why I picked a 2 here, because when I square it, I'll get a 4 in front of the tangent. So this substitution is going to take care of the x. Now let's take care of the dx. We take the derivative of 2 tan theta and get 2 secant squared theta d theta. And so let me take these and put them in here. So don't forget the dx. I'm going to put that right up on top. 2 secant squared theta d theta. And then downstairs, I got the 4. And when I square my x, I'm going to get 4 tangent squared theta. So we write a new integral in terms of the new variable. Now look under the radical sign. I got that common factor of 4 that I'm going to pull out. Leave me with a 1 plus tan squared. And that's the trig identity I wanted to use. That's what I wrote over here. Tangent squared theta plus 1 is secant squared. So we're able to swap out 2 terms for 1 term. Let me swing it all the way back over to here. Keep my 2 secant squared theta on top. Swap out the 1 plus tangent squared for a secant squared. And then in the next step, we're going to take the square root of that. So it's going to put me a 2 secant theta on the bottom. And we can cancel. Of course, we cancel the 2's and cancel one of the secants. So we're left integrating the secant of theta. That's one of the ones that I put on the previous page. Remember, that's the one that's the natural log of the absolute value of the secant of theta plus the tangent of theta. Okay, we'll be done once we get our antiderivative back in terms of the original variable. And we can get that from our original substitution. Solve that equation for tan theta, and I have x over 2 is the tangent of theta. So that's going to go in right here. If you know the trig value of an angle, then you know all 6 of them. And we have a triangle that can help us remember that. A right triangle trigonometry. If I put a angle theta there, the tangent is the ratio of the opposite over the adjacent. So I can put my opposite side to have length x, my adjacent side to have length 2. We're going to need the secant of that angle. The secant is the hypotenuse over the adjacent. So we'll do the Pythagorean theorem to find the hypotenuse. Leg squared plus leg squared is hypotenuse squared. So 4 plus x squared is hypotenuse squared, which gives us this term as the hypotenuse. And it's no small coincidence that that's that. That'll always happen. The third side will always be that term in your integrand. And now we take these and substitute them in. Secant of theta is the hypotenuse over the adjacent. And the tangent we got is x over 2. And there she be. Okay, let's look at the next one. All right, now if this were next to the first power on top and an x squared under the radical, then I can do a u du term. But the fact that I've got too large of a power on top keeps me from treating this as a u du integral. If that x weren't there at all, if this were just a constant on top, then that's already an inverse sine integral. But the x is there, we got to handle it. And the way to handle it is to try to get rid of it with this substitution. We chose the sine because I've got the variable behind the minus sign, and I'm going to try to get the stuff under the radical to look like a 1 minus sign squared. So I'm going to try to get this to look like 9 minus 9 sine squared. And that's why I chose the 3. The x is going to be squared, and I need the same number in front of this as I have out here. I'm going to put that in for each x, but now I need to generate my dx term. So let's go back to this line and take the derivative of both sides. That gives me dx is 3 cosine theta d theta. Now let's put it in and see if that does indeed take care of that radical sign. So we've got an x squared on top. I'll go ahead and square it and get 9 sine squared theta. We're going to put that in where the x squared is on the bottom, right here. Then we're going to take the square root of it. And dx is 3 cosine theta d theta. Now under that radical sign, I'm going to factor out the 9. There's my 1 minus sine squared. One minus sine squared is cosine squared. So I'm going to put cosine squared in under that radical there. I have 9 times cosine squared. That's what I wanted to happen. I wanted to go from 2 terms being subtracted to a product. I can take the square root of each term in a product. So I get a 3 cosine theta here. In the next step, I'm going to cancel it here. And I'm left integrating 9 times sine squared of theta. We pull out the 9. Then we remember from chapter 6 that the integral of sine squared is theta divided by 2 minus the sine of 2 theta divided by 4. But I want to get everything in terms of angle theta, so I'm going to use yet another trig identity right here, that the sine of 2 theta is 2 times the sine of theta times the cosine of theta. That'll make it easier for me when I substitute out my thetas. So that's kind of a handy trig identity to remember. Sine of 2 theta is 2 sine theta cosine theta. Now we need substitutions for the sine of theta, the cosine of theta, and theta itself. And we get them from back here. The sine of theta is x over 3. That means theta itself is the inverse sine of x over 3. And now to get the cosine of theta, I'll draw my right triangle. The sine is the opposite side over the hypotenuse. And then this squared plus that squared is hypotenuse squared. So here I'm going to need my 9 minus x squared, same as up in the integral. So now the cosine of that angle theta is the adjacent over the hypotenuse. And so let's go up here and put our answer in terms of x. I have theta, which I said was the inverse sine of x over 3. Then it's divided by 2. Here I'm going to cancel the 2 and the 4. So I'm going to put a 2 down here. The sine of theta is x over 3. And the cosine of theta is the square root of 9 minus x squared over 3. Close that up and add a plus c. Okay, got kind of tangled up in there. Okay. Okay, so we've done the first two substitutions. We did the one with the plus sign to go with the tangent. The minus sign behind the variable squared behind the minus sign gives us a sign. So now we're going to do the one with the variable squared in front of the minus sign. So the suggestion is to use a secant so that we can use the identity that secant squared minus 1 is equal to tangent squared. Okay, so x is going to be 5 secant theta so that when you square it, you get the 25 right here. Then I need the dx, so I take the derivative of that. The derivative of a secant is secant theta times tangent theta times d theta. Okay, I'm going to come down here this time. I think this problem takes a little bit more room. So we're going to substitute in here. X squared will be 25 secant squared. Then I subtract that 25 and put the radical sign back on it. X to the fourth will be 5 to the fourth. That's 25 times 25, so that's 625 secant to the fourth. And then dx was the 5 secant theta tan theta d theta. Okay, so the main thing we're looking at now is the stuff under the radical sign. We got the common factor of 25 that we're going to pull that out. That leaves us with secant squared theta minus 1. Still have the 625 secant to the fourth on the bottom. And then the 5 secant theta tan theta on top. But secant squared theta minus 1 is our tangent squared theta. So we have 25 tangent squared theta under the radical sign. 625 secant to the fourth theta in the denominator. And then the 5 secant theta tan theta d theta on top. We're going to pull that way up here. We'll go to the top line now. Okay, so next, we're going to take the square root of this and get 5 tangent of theta. So I have 5 tan theta, 625 secant to the fourth of theta, and then up here on top, 5 secant theta, tan theta, d theta. So let's collect our numbers. 5 times 5 is 25. 25 goes into 625 25 times. Pull that way out front. One of these secants cancels with one of these. So now I'm down to the third power here, and a tangent squared on top. Here we look for a u du integral, but I don't have it because if u is the secant, the du is going to be a secant tangent, and I have a tangent squared. So I think what I'm going to do is go to sines and cosines and see how this reduces for me. That's a sine squared over a cosine squared. And a secant is 1 over cosine, so I have a 1 over cosine cubed. Now we're going to do the flip and multiply step. Tip that over and multiply. Here's our sine squared over cosine squared. And up here, I've got a cosine cubed. So knock off 2 of those with 2 of those. And so I have a sine squared times a cosine. I'm going to have to continue this on another piece of paper. So let me move it over to here. Let's just recopy it. Goes into the first. Again, we look for a u/du integral, and we have it because the derivative of the sine is a cosine. So we're going to take u to be the sine of theta. That leaves me with cosine of theta d theta is the du. So there's my du. And so we have 1 over 25, the integral of u squared times du. Okay, so that's 1 over 25 times u cubed over 3. Now we need to go all the way back, get it in terms of theta, go from theta back to x. So let's write that as 1 over 75. That's going to be a sine cubed of theta. Now let's go back and figure out from there how theta is related to x. So that comes back from our original substitution. X was 5 secant of theta. So x over 5 is equal to the secant of theta. I need the sine, so let's draw a triangle. That's angle theta. Secant is hypotenuse over adjacent. And then this squared plus that squared is x squared. So this is going to be 5 squared plus b squared is x squared. So b squared is x squared minus 25. That's here. Again, that was the term that was in our original integral. That'll always be part of your triangle, if you did things right. Now, the sine is opposite over hypotenuse. So opposite is the square root of x squared minus 25. Hypotenuse is x. And then I got to put the cubed on it. And there's our antiderivative. Okay, so we've got 3 more to go here. The next one has a 1 minus x squared under the radical sign, and it has an x squared on the bottom. So it's not a u/du integral. I don't have an x to the first power out here anywhere. So I've got to look for another way to get rid of the radical sign. The x is behind the minus sign. So our strategy there, when the x is behind the minus sign, is to choose a sign and hope to use this Pythagorean identity. My a is just 1, so I'm going to pick x just to be sine of theta. Don't forget the dx term. Derivative sine is a cosine. And now let's put everything in. X squared is going to be a sine squared. I get 1 minus sine squared theta under the radical sign. I have a sine squared on the bottom. And then my dx term is the cosine of theta, d theta. Okay, so there's our Pythagorean identity. 1 minus sine squared is cosine squared. And the integral of cosine squared is a cosine. I'm going to take this cosine to the first power, multiply it with this cosine to the first power, and give me a cosine squared on top. Now that's not a UDU integral because I have a cosine squared on top. So what I'm going to do is rewrite this as a cotangent squared. I don't know how to integrate a cotangent squared, but I do know how to integrate a cosecant squared. The function whose derivative is a cosecant squared is a cotangent. So I've got to get this in terms of cosecants. Well, I have a Pythagorean identity for cotangent squared. Here's how we remember it. We know sine squared plus cosine squared is 1. And so if I want a cotangent, I want to divide that by sine squared. So let's divide everything by sine squared. And that says 1 plus cotangent squared is 1 over sine squared. That one's the cosecant squared. So I'm going to replace cotangent squared with cosecant squared minus 1. You know, that's the same way we integrate a tangent squared. To integrate a tangent squared, we change tangent squared to secant squared minus 1 because we know how to integrate a secant squared. The integral of cosecant squared is a negative cotangent, and then the integral of that one is just going to be a theta. Now let's get this back in terms of our original variable by going back here. X is the sine of theta. So let's draw a triangle. And think of that x as being an x over 1, so opposite over the hypotenuse. And then this side, that squared plus that squared has to be 1. So I want my 1 minus x squared here. And then from this picture, we can get the cotangent of angle theta. Cotangent is adjacent over opposite. And then we need theta. From here, we can get theta. Theta is the inverse sine of x. Okay? That one worked out pretty well, but you had to remember how to integrate a cotangent squared by converting it to cosecants. So over here, let's just remember, let's add these to our remember integrals. We know how to integrate a secant squared. The integral of secant squared is a tangent. And so we know how to integrate a cosecant squared. That's going to be a cotangent with a minus sign. Okay, now let me show you how to handle things when I've got a number in front of my variable. We'll take this initial step and rewrite 9x squared as 3x all squared. So if you want, you can do a UDU substitution and change this all in terms of U, or we can kind of do it in one shot. I've got a plus sign under the square root. So with the plus sign, I'm going to make a tangent substitution. The a is the term out here. So in our problem, a is 4. So I'm going to say let 3x equal 4 times the tangent of theta. Let me do it over here this time. So x is 4/3 tangent theta, and dx is 4/3 times secant squared theta d theta. And now let's put each x as a 4/3 tan theta, so we'll have 4/3 tan theta all cubed. 3x is 4 tan theta, so here we'll have 16 tan squared theta plus 16, and then we put our dx in there. Okay, so x we said was 4/3 tan theta all cubed. 3x is 4 tan theta, so 3x squared is 16 tan squared theta. And those two terms are under the radical sign. And dx is 4/3 secant squared theta d theta. Let's get the numbers out of the way right off the bat. This is going to be a 4/3 cubed. Multiplied with another 4/3 gives me a 4/3 to the 4th out here. Then I'm going to have a tan cubed secant squared there, and then we're going to simplify the radical. So here's the 4/3 to the 4th. Then tan cubed theta, secant squared theta. And under the radical, I factor out the 16, leave me with a tangent squared theta plus 1. That's the trig identity that becomes secant squared. So in the next step, I'm going to replace this with secant squared. Let's go ahead and get this number. 4 to the 4th. Oh, whose stupid idea was that? 4 times 4 is 16. 16 times 16 is 256. 3 to the 4th is 9 times 9 is 81. Tan cubed theta, secant squared theta. This becomes 16 times secant squared. Under the radical sign. So in the next step, I take the square root of 16 secant squared. So here's my 256 over 81. Tan cubed theta, secant squared theta. And this is 4 secant theta. So we're going to knock out a secant. I'm going to come over here and divide the 4 into 256. I think that goes 64 times. And so I have tan cubed. I knocked out 1 power of secant, so I still have a secant up here. So this is where all the practice on the trig integrals comes in. Remember, if there's an odd power on a secant, you pull out secant tangent and hope to set up a du integral. So I got an odd power on a secant. I'm going to pull out a secant tangent and put it next to the d theta. So over here, I'll have a tangent squared left. But it's not a u-du integral because the derivative of tangent is not secant tangent. The derivative of a secant is secant tangent. So what we're going to do is replace tangent squared with secant squared minus 1. Now I have a u-du integral. Let's take u to be secant, and du is secant tangent. That means the integral we've got left to do is just u squared minus 1 times du. Which is a u cubed over 3 minus 3, or minus u. Oops. Each u is a secant of theta. But don't stop there. We need to get this back in terms of x. So let's look at our original substitution. I did that way up here. 3x is equal to 4 tan theta. So I'm going to say if 3x is equal to 4 tan theta, 3x over 4 is the tangent of theta. Let's draw the right triangle to get our secant out of that. Tangent is opposite over adjacent. And so leg squared plus leg squared is hypotenuse squared. Gives me that this side is 9x squared plus 16. Again, what we had up here. But we can get the secant of theta by taking hypotenuse over adjacent. So hypotenuse, 9x squared plus 16 over 4 cubed, then divided by 3. Minus our secant, which is 9x squared plus 16 over 4. Kind of messy, sorry about that. And I kind of bled into this problem, so we'll do that problem on a separate sheet of paper. That was a long one. Okay, so let me copy this problem down on the next sheet of paper. That's problem number 6. I lost my 6. Okay, I'm going to give it its own sheet of paper. There we go. Here's what problem number 6 was. The integral of 1 over square root of x squared plus 6x. So, we've got next to the first power here. We don't have a constant the way we had in here. So when that happens, I think one thing that might hopefully be obvious to you is that we're going to complete the square steps to this, so that I either have the sum of 2 squares or the difference of 2 squares. So let's complete the square. We take our stuff under the radical sign, we add a number, take it back out. And remember, we take half of the middle term and then square it. Put it there and there. So half of 6 is 3, 3 squared is 9. And 9 is a number that has 2 like factors that add to 6. That's what makes that a perfect square. So this is going to factor as x plus 3 all squared minus 9. That's under the radical sign. So it looks like something squared minus a number squared. But the variable is in front of the minus sign, right here. So we're going to choose the stuff in the parentheses to be 3 times the secant of theta. Take x minus 3 to equal 3 secant of theta, so that hopefully we'll get this term in there. Now take the derivative of both sides. The derivative of the left gives me the dx. The derivative of the right gives me 3 secant theta, tan theta, d theta. And now we're going to substitute that in. X plus 3 is 3 secant theta, so x plus 3 squared is 9 secant squared theta. That's under the radical sign. Dx is all of this, 3 secant theta, tan theta, d theta. Now here's where we factor out the 9, and our second factor will be secant squared minus 1. That's our trig identity. 9 times secant squared minus 1 is going to give us 9 times tangent squared. So let's put 9 tangent squared down here. But it's under the radical sign, so in the next step we'll take the square root of it. So I'm going to get 3 tan theta on the bottom. Let's just slide that over. And there, cancel the 3, cancel the tangent of theta, and we're left integrating secant of theta. That's one we know. That one's a natural log of the secant plus the tangent. Now let's get this back in terms of x. So let's go back to the beginning, right here, and write that as a ratio. X plus 3 divided by 3 is equal to the secant of theta. Right here, x plus 3 divided by 3. To get this one, draw the right triangle. Secant is hypotenuse over the adjacent. And so this one should be the x plus 3 squared minus 9. Using that, the tangent is opposite over adjacent. Let's fill them in. Secant was the x plus 3 over 3 plus tangent is the square root over 3. Square root of x plus 3 squared minus 9 all over 3 plus c. Okay, good little practice there. What you should spend your time on now is learning what substitution goes where. Again, you've got to learn these. And then as you're doing integrals and come up with something that you think you should know, make you a list of things that you need to remember. And keep that next to you and learn them and learn them and learn them and learn them, because they'll keep showing up. Okay, I'm going to end that here. You guys keep practicing.